In this recording, we're going to look at the more quantitative aspect of our redox reaction. And by that, I mean we're going to look at calculating the electrochemical potential for both standard cells, where we have our standard conditions, or non-standard cells, in which case we are going to use something called the Nernst equation. To understand what we're calculating, we have to understand the electromotive force. If we think about electrons moving through a wire, we have to have work be done in order for those electrons to move through that system. We have motion, so therefore work must be done. We can think of this similar to how water moves from low pressure to high pressure. We're going to see that in our electron system, that the electrons are going to move from higher potential to a lower potential. You could think about this like a waterfall. So as this water falls, the height from which it falls determines the energy right before it hits the surface here. The higher the waterfall is, the more potential energy we observe at the top of the waterfall, and the more energy, kinetic energy, we have at the bottom of the waterfall. So our total energy available will be greater when our waterfall is taller. That's true for these electrons as well. If we have a greater difference between our reactant and product in the chemical potential, then we're going to see that we have more energy that we can get out of that system. So what causes this pressure, this so-called pressure in an electrical circuit? First, I want to go over a little bit of terminology with you. It's commonplace to think of voltage and current as the same. When we talk about the outlets in our home, we say they're 120 volts, and they're actually, most of them are 60 amp. Those two measurements are measuring two different things. Voltage is not actually measuring electron flow, but the possibility of electron flow, and it will tell us information about the energy available. If we go back to our analogy, we can think about, again, water as electrons, and that water moving through a pipe analogous to electrons moving through a wire. The greater pressure we have here, the greater potential energy we have in the water, and the faster it'll flow through our system. In our electrical analogy, the greater the chemical potential or our electric potential here at the anode, which again, the anode is where oxidation occurs, the greater potential we have from our anode to our cathode, the more energy we're going to see in those electrons passing through the wire. So this electric potential is really our voltage, and it's a measure of the electromotive force. So how fast the electrons will move through that water. Current, on the other hand, is actually measuring the electron flow. We measure it in amps. An amp is equal to 1 coulomb per second. So if we sat there and watched the electrons pass by, electrons have a charge of something times 10 to the minus 19th coulombs. So we could tally up those electrons as they're zooming past us and then multiply that by the charge in coulombs to figure out how many coulombs per second we have. If we have 1 mole of electrons pass, we're going to see that we have 96,485 coulombs. And so 1 mole of electrons is equivalent to this 96,500-ish coulombs. Voltage, on the other hand, again, is looking at the potential difference between where our electrons start and where they end up. If we have high potential going to a lower potential, like we would expect, the electrons will flow spontaneously from that high potential to a low potential. We measure the potential in volts, and let me follow that up with, if we were looking at a system where we start at low potential and go to high potential, that reaction would not be spontaneous. We measure the potential in volts. 1 volt is equal to or equivalent to 1 joule of energy per coulomb of charge. So we normalize this based on the charge of the substance we're looking at. And since we're looking at electrons, most often we're going to be using this Faraday's constant to figure out how many coulombs based on the number of electrons transferred. And we'll go over this in the next recording. And then the amount of charge, like we said, contained in 1 mole of electrons is roughly that 96,500 coulombs, which we call a Faraday. That electromotive force we can determine based on a table of standard potentials, specifically standard reduction potentials. So this came from your guys' textbook. It's table 20.1. This was the old edition. And actually it might be 19.1. I think I updated this. Regardless, if we look, notice that each reaction, you look very closely, we have a substance, a material, and we're adding electrons to it. This adding electrons would be reduction, and hence we call this a standard reduction potential. And then over here we have our products, what we form, and then the potential associated with that. And again, that potential is going to be measured in volts. Up here at the top, we see 2.87, and then as we go down, we see negative 3.04. What these numbers tell us is the ability of the substance to steal or give electrons. If we're at the top of the chart, the more positive values are going to be more likely to accept electrons and therefore be reduced. If they are reducing, then it means that they're going to be an oxidizing agent. So these substances here at the top, they're our strongest oxidizing agent. They have the most positive potential. The substance at the bottom, they have negative potentials, which means they're very willing to give up their electrons or be oxidized. That means they're going to be very good reducing agents because they're going to cause the substance to be reduced, and they're going to be terrible oxidizing agents. These values given in this table are under standard conditions, which again means that if we have a solution, an aqueous solution, it's going to be at a concentration of 1 molar. If we're looking at a gas, it's going to be at a pressure of 1 atmosphere. The temperature for these reactions is going to be the standard temperature, 25 degrees Celsius or 298 Kelvin. And then as long as we keep it in these conditions, then that gives us the standard potential of our cell. To calculate the standard potential of the cell, we need to look at the difference in the energy potentials, electron potentials for our specific substances. So here we have our half reactions. We would look at 2 half reactions we need to combine and then take the absolute difference between those 2 half reaction potentials. So how do we find the standard potential? Well, again, each electrode has its own potential that we've measured against that standard hydrogen electrode we talked about last time. The standard hydrogen electrode, because it's used as a reference, it has 0 for its standard potential. And then all of the other values given in that table are based relative to this. To calculate the potential of our cell, we want to combine the potential for both the oxidation half reaction and the reduction half reaction. We run into a bit of a problem with this because the table gives us the reduction potential, not the oxidation potential. But if we reverse the reaction, then that would tell us our oxidation potential. And when we reverse reactions, we reverse the sign on the reduction potential. So we'll do a few examples of this. So when we write out that redox reaction, we're going to have 2 half reactions, one where we have reduction and one where we have oxidation. And then to figure out the E of our cell, we have to know the oxidation potential. So what we can do is look up the reduction potential given in the table and then change the sign for the oxidation half reaction. Once we've done that, then we can simply add these 2 together. Another thing you can do is you can use this equation here, that E cell is going to be equal to the reduction potential of the cathode minus the reduction potential of the anode. And then you don't have to worry about losing sign. You just have to be able to decide which half reaction is reduction occurring. That will be the reaction that's occurring at the cathode. And what half cell reaction is occurring at the anode, which that reaction should be the one where oxidation is occurring. We don't care about how much material is there. So even if you have a balanced equation, we're going to ignore the coefficients. And we're only just going to try to identify what the half cell reaction is and then look up the potential in that standard reduction potential table. So the amount of material there will not affect the voltage. That difference remains the same regardless of how many electrons get transferred. If we go back to that waterfall analogy, that water is going to fall the same distance regardless of how much water falls over the edge. So now let's look at an example. And the first example we're going to do is that Daniell cell where we have copper and zinc. Our reaction for that spontaneous Daniell cell was where we had copper ions in solution stealing electrons from the zinc to reduce the copper and oxidize the zinc. If we look up the standard reduction potential for these two reactions, copper is shown here. It has an oxidation potential of 0.337 or 0.34. And then our reduction potential for the zinc half reaction is down here. It has a more negative reduction potential, meaning it's going to want to give up its electrons, and the copper, more positive reduction potential, is going to take those electrons. So again, this half reaction here, we're going to see that it goes in the opposite direction. And when it goes in the opposite direction, that means I need to change the sign here from a negative to a positive. And then what I would get here is 1.1 volts. Alternatively, we could use that expression where E cell equals E anode minus E cathode. And when we do that, our anode, again, is where oxidation is occurring. Good, I misspoke. So our E cell is equal to so we have E cathode minus E anode. The cathode is where reduction occurs. So we have our copper taking those electrons, and the potential is 0.34. And then we subtract the potential of our anode, which is where oxidation occurs, which is our zinc electrode, and that was negative 0.076. So E cathode minus E anode gives us the same answer. So whichever way you feel more comfortable with, stick with that way. If you want to memorize E cell equals E cathode minus E anode, that would be fine. Or you could look at the reaction, see which one is your oxidation reaction, change the direction of that reaction by changing the sign, and then add those two together. Let's do one more example. So this time we're going to try to reinforce some of what we learned earlier. So we're going to create a battery, a galvanic cell, made of aluminum and nickel and their solutions. Nickel is here. It has a reduction potential of negative 0.25. Our aluminum is way down here, and it has a reduction potential of negative 1.66. So before we go any further, I want you to tell me which will be oxidized and which will be reduced. Because the aluminum has the more negative reduction potential, that means it's going to be the species that's oxidized. It wants to give up those electrons. So that means when I calculate my standard reduction potential, we are going to want to flip this reaction and flip the sign. Again, or I'm going to take this negative 0.25 and subtract negative 1.66. Because this is a galvanic cell and the reaction occurs spontaneously, we should end up with a positive reduction potential. So we're going to find the cathode, find the anode, and we could even do that now. Here, where reduction occurs, that's going to be our cathode. And then down here, where oxidation occurs, that's going to be our anode. And then we want to figure out our oxidizing agent and reducing agent. And this is review from 141. The oxidizing agent and reducing agent are the species that cause oxidation or cause reduction. So whatever is reduced is going to be our oxidizing agent, and whatever is oxidized is going to be our reducing agent. What is oxidized is causing something else to be reduced, hence we call it the reducing agent. We're also going to be able to write the overall reaction, determine the direction of the electron flow, the number of electrons that are transferred in this redox reaction, and our E naught of cell, so the cell potential or the cell voltage. So first, again, I'm just going to copy down those half reactions from the table. And like I already mentioned, this is a galvanic cell, so it has to be that the reaction is spontaneous, and our delta G must be negative. Since delta G equals negative NF delta E, that means that our E cell must be a positive value in order for this product to be negative. So here we have our reduction potentials listed, and if we wanted to add up these reactions, we would need to have the same number of electrons transferred. The other thing is we can see based on the reduction potentials, like we did on the previous slide, that the aluminum should be oxidized and the nickel should be reduced, making the nickel the cathode and the aluminum the anode. So now when I draw my cell, I'm able to determine the direction of the electron flow. Since the aluminum is losing its electrons, donating those to the nickel, it should be that our electrons move from the aluminum electrode to the nickel electrode. Nickel ions in solution then will interact with those incoming electrons and get reduced and be plated onto this nickel electrode. If we wanted to calculate our potential, again, we could use this equation, E cathode minus E anode, and that gives us plus 1.41, or like we did earlier, you could reverse the sign here, reverse the direction here, reverse the sign, and then if we do negative 0.25 plus 1.66, we would again end up calculating 1.41 for our electron volts. For our overall reaction, like I mentioned, we're going to need to have the same number of electrons on both of our half reactions. So we need this 2 and 3 to be the same number. The lowest common multiple for 2 and 3 is 6, which means I need to multiply my first reaction, the reduction reaction, by 3. So I would end up with 3 nickel, 6 electrons, and 3 nickel. And then down here, my aluminum half reaction, I would need to multiply by 2. So I would end up with 2 aluminum 3 plus 6 electrons going to aluminum solid. But again, this is going in the opposite direction. So this would be my reactant, and these would be my products. So then overall, what we have is we have 3 nickel and 2 aluminum. Again, here are my reactants, going to 3 nickel, solid nickel, and 2 aluminum 3 plus. Those 6 electrons that we had are going to cancel. Then to identify the oxidizing and reducing agent, we want to, our oxidizing agent is going to be the substance that's reduced. And so here, the nickel 2 plus, since it gets reduced, ooh, that was a little sloppy. Since it was reduced, that makes it the oxidizing agent. The aluminum, the solid aluminum, on the other hand, it was oxidized, and that makes it our reducing agent. So again, your oxidizing and reducing agents have to be reactants. Whatever is oxidized is your reducing agent. Whatever is reduced is your oxidizing agent. So now I want you guys to try on your own to calculate the standard reduction potential. And we want it for this reaction here, where we have magnesium and liquid bromine, creating magnesium ions and 2 bromine ions. Again, we don't care about the coefficients. We just need our half reactions, and then you're given the standard reduction potential for both of those half reactions. So our first half reaction for the magnesium, where we have Mg2 plus going to Mg, as shown here, there my oxidation state goes up, which means that this must be oxidation. And what I see in the table is that the magnesium 2+ can take 2 electrons and form magnesium solid. So again, this is going to be, since it's a hot oxidation half reaction, it's going to be going in the opposite direction. So we're going to flip that direction, and then I've changed the sign from negative 2.37 to positive 2.37. Our other half reaction is with the bromine, and the bromine liquid takes 2 electrons and becomes 2 Br-. These standard reduction potentials will be given to you always in the problems that you're given, or you'll be given a table where you can look them up. And so then here, our standard reduction potential for that bromine half reaction is 1.09. So now that we have our 2 half cell reactions and we see which direction they're going, we can add those 2 up and we get 3.46. Again, alternatively, you can use E cell equals E cathode minus E anode, and we see here again that the magnesium is where oxidation occurs, so that's our anode, and the cathode is where reduction occurs, so that would be equal to 1.09 minus our reduction potential for the magnesium, which we were told was negative 2.37, and we still get the 3.46. Not all of our cells are going to be at 1 molar concentration or 1 atmosphere for pressure, and they might not be at 298 K. So we could see changes in both the concentration and the temperature. Therefore, the measured potential that we measure in the lab, the potential we measure in the lab, is going to change. The Nernst equation allows us to use temperature and concentration in the form of Q to determine or predict our voltage, our standard reduction potential of our, and I should just scratch that. It lets us calculate the potential of the cell if we're not under standard conditions. And we do this by using the value under standard conditions and then altering it slightly, just like we did before with delta G. So we see that the potential of our cell is equal to the standard potential of our cell minus R, T, and F, ln of Q. R is our ideal gas constant, 8.314 joules per Kelvin times moles. T is our temperature given in Kelvin. N is our number of electrons transferred. So that's a new one. Typically it's moles of our substance, but in this case it's moles of electrons. So we'll use our balanced equation to figure out how many total electrons get transferred, and that's what we'll plug in here. And then F is our Faraday constant, that 96,500 coulombs per mole. Q, remember, is our equilibrium constant when we're not at equilibrium. And since we're under non-standard conditions, we wouldn't be at equilibrium. And Q is going to be the concentration of the products divided by the concentration of the reactants. If we do have any sub-coefficients in our balanced equation, we would put those coefficients here as exponents. So let's say that we have a cell. Just kidding, that's the next slide. So we can take this equation and we can combine the R, T, and N constants, R, T, and F constants, and then we can either express the Nernst equation as the natural log or log. But it has to be at 298 K for these next two expressions to be true. So we can simplify it to say that E of our cell is equal to E naught minus 0.0257 over N. And again, this 0.257 is R times T, where T is 298 K, divided by that 96,500. And then if we're in the log-based scale, we would have that number, and we would take the natural log of Q. If we want to use the log-based 10 scale, then we would multiply that 0.257 by 2.1-ish, and that would give us 0.0592, and then we could take the log of Q. You can use these interchangeably. Again, it won't matter which version you use, you will still calculate the same potential for the cell. So now let's consider we have a battery, and it's nickel and aluminum, where the aluminum concentration is 0.0010 molar and the nickel concentration is 0.05 molar. If we look at our standard reduction potential table, we see that the aluminum has a standard reduction potential of 1.66, and the nickel has a standard reduction potential, and that was negative 1.66, of negative 0.25. So that was the example we looked at earlier. And we decided from these potentials that the aluminum, being more negative, wants to get rid of some negatives, so it's going to be oxidized. And the nickel is going to want to take those electrons. It has a more positive electron potential compared to the aluminum, so it will take those electrons and be reduced. Our concentrations are not 1 molar, and so we're going to have to take that E naught that we calculated, which again was anode minus cathode, and when we plugged that in, we calculated a standard reduction potential of 1.41 volts. We're going to alter this a little bit using the Nernst equation. So we're going to subtract from this negative RT, or we're going to subtract from it RT over NF times ln of Q. And Q is going to be products over reactants. So again, these were the reduction potentials that we observed. For our balanced equation, we would need to multiply this first reaction by 3, the second reaction by 2. So that's going to give us a total of 6 electrons. And now we have our balanced equation. From this balanced equation, we can write our Q. Q, being products divided by reactants, would be the aluminum squared times the concentration of the nickel, but the nickel's a solid, so we leave that out of our expression. Then we would divide that by our reactants. Again, the aluminum here is a solid, and we don't include solids. So it'd just be the concentration of the nickel 2 plus cubed. Notice when we did this that we didn't do anything to the cell potential. We never multiply that cell potential, just as we can't change the height of the waterfall. Now we know that our E cell is 1.41. We have our balanced equation, we know what Q is, and that N was equal to 6. That was the number of electrons transferred, because we needed to multiply the nickel half reaction by 3, and we can see that the oxidation state changed by 2. So that 2 times 3 gives us 6 electrons transferred. And we determined again that Q was products over reactants, and then we raised those to the stoichiometric coefficients. Plugging it all in, our E cell minus that RT over F, which is equal to 0.0257. We divide that by N, which in this case is 6, and then we take the natural log of our aluminum concentration squared divided by the nickel concentration cubed. That gets us 1.41 minus 0.00428 times the natural log of 8 times 10 to the minus 6. So our cell potential under these non-standard conditions is actually going to be a little bit higher because of the concentration differences. We get 1.46 rather than the 1.41. Now it's time for you to try. This time we're looking at silver ions reducing to solid silver, and the aluminum giving up some electrons and being oxidized to aluminum 3+. So don't forget that the Nernst equation that you want to use is E cell is going to be equal to our standard reduction potential of our cell, or our standard potential of our cell, E naught of cell, minus RT over NF ln of Q, which we can simplify to be our standard potential of our cell minus 0.0257 over the number of electrons transferred times the natural log of Q. Q is products over reactants. You're given the concentration of the aluminum. You're given the concentration of the silver. Make sure you square, cube, quadruple where it's appropriate, and you should get one of these 4 answers here for the cell potential. So looking at this reaction here, I can see that the aluminum going to aluminum 3+, that's going to require that I lose 3 electrons. Or we could look at these 3 silver ions, and we can see that those 3 silver ions are going to require 3 times 1 electron. Our N value then is going to be equal to 3. And then Q, products over reactants, our products are the silver, which we would ignore, and then the aluminum 3+, it has a coefficient of 1, divided by our reactants. We have 3 of the silver ions, so we need to multiply that silver ion concentration by 3, and then we wouldn't include the aluminum. Our silver ion concentration is 0.010, so that will plug in here, down here. And then our 0.2 molar aluminum gets plugged in here. So then what we get is 2.46. And we were told that just right here, that the standard reduction potential for this cell is 2.46. You might have to calculate it based on the half reactions. So you'd have to look at the aluminum plus 3 or minus 3 aluminum going to aluminum 3+ minus 3 electrons. And then that would get subtracted from the silver half cell reaction. So you would be able to look at both of those potentials and do like we did at the beginning, where you could calculate E naught of your cell. And then we subtract from that 0.0857, which is yes, good. So here I have the log base cell example, and here I have the natural log example. So this would be the 0.0592 divided by 3 times the natural log of 200,000 would give us 2.46 minus 0.1046. This here you would also see that 0.0937 times the log of 0.02 divided by 0.01 cubed would also give us 0.1046, and so we calculate 2.355 volts, which is D. And again, we can see that the reduction potential is positive, and so it would be a spontaneous reaction. Concentration cells are batteries, galvanic cells, where you have the same metal in both the anode and the cathode. But the concentrations are different, and when the concentrations are different, we can still get a potential, and we would calculate that just based on the Nernst equation. So the driving force here is not that one metal is more electroactive than the other, but rather we have a difference in concentration. We would like to take this copper solution that has a lower concentration and increase the concentration of that copper 2+. We could do that by taking some of this solid copper, oxidizing it to become copper 2+. Or we could reduce the concentration of the copper here so that we have equal concentrations on both sides. And the way that we could do this is to take the copper 2+ that's in solution and reduce it so that it plates onto the electrode. So we're going to see that electrons are going to flow from the cell that contains the lower metal ion concentration to the cell that contains the higher metal ion concentration. And this is again because the oxidation reaction is going to increase the ion concentration, while the reduction reaction is going to reduce the concentration of that ion. We would still use the Nernst equation to calculate this, where we have that E of the cell is going to be equal to our standard potential, our cell under standard conditions, minus 0.0257 over N times the ln of Q. In this case, the number of electrons transferred, because we have copper going to copper 2+, we could see that in order for that to happen, that copper has to give up 2 electrons. Or over here in this cell, we have the copper 2+, accepting those 2 electrons and becoming copper. So we know that our N value is going to be 2. E naught of our cell, we would take the reduction potential E at the cathode minus E minus the anode, E naught of the anode, and the reduction potential at the cathode is the same as the reduction potential at the anode. So my E naught cell is going to be equal to 0. Copper has the same electrical reactivity. And then our Q is just going to be products over reactants. Our overall reaction is going to be copper 2 plus from our reduction half reaction plus solid copper from our oxidation half reaction, forming copper 2 plus and copper. This copper here is going to be the one at lower concentration. As the reaction proceeds forward, it will increase the amount of copper in this solution. And then this copper ion on our reactant slide, that's our more concentrated copper. We want that copper ion concentration to go down as the reaction progresses, which would happen if this spontaneously moved in the forward direction. So that means our Q here is going to be products over reactants. Our products are going to be the copper ion at lower concentration, and again we ignore that solid, divided by our reactant, which will be the copper at higher concentration. So that will be equal to 0.010 molar divided by 2 molar. If we take the natural log of 0.010 divided by 2, we get negative 5.298. Our standard reduction potential was 0. That negative 0.258 times the 0.257 divided by 2 gives us negative 0.068. Subtracting that negative value gets us to the measured potential of 0.068. So from this video, I hope that you came to learn how to calculate your standard reduction potentials and what the standard reduction potential means. Again, it's a potential, so you're looking at potential energy, and it's the ability, the amount of energy stored in those electrons. So the higher that the greater that difference, the higher the voltage will be on your battery, and you'll be able to power devices that require more electric energy. You should know your standard conditions, 1 molar, 1 atmosphere, for electrochemical cells, and how you can use them to determine the cell potentials. You will be given, or you can look up, the standard reduction potential for our half reactions, and then take the difference between those reduction potentials to find your reduction potential under standard conditions for your cell, or E cell. And then that's 75, determining the cell voltages using the standard reduction potentials. And then we also talked about the Nernst equation, where you're under non-standard conditions, whether it's temperature or concentration. And we primarily focused on concentration. You have those two different forms of the Nernst equation, E cell equaling E naught of your cell minus 0.0257 over N times the natural log of Q, or E cell equaling E naught of your cell minus 0.0592 divided by N times the log of Q. Great, so let us know if you have any questions.